Hello, am I audible? Can people respond? Can any one of you confirm? Okay, so good evening everyone. I am Shruti. I am the PMRFTA for this course, the NPTEL course which is Symmetry and Group Theory. I welcome you all. So today we are having our first live session. So this is a long course, a 12-week course, and we will have live sessions every Monday as it has been informed to you, right? So I'll be discussing like assignments which have been given in the previous week. So maybe today I'll be discussing week 0 and week 1 content possibly, and that's all. So have you guys gone through the week 1 lectures? Hello? Okay, Vinita. Have you watched all the lectures? Like the course is already there, right? Vinita, where are you from? Sandeep, Dipti, Haryana. Okay, nice. Are you in MSc? You are doing MSc right now or in BSc? I'm just asking, like, I want to know the level of the students in the course, whether they are in BSc or MSc or they have completed BSc, MSc. Completed MSc. Great, great. What about Sandeep, Monica, Maya? MSc. Okay. Okay. So completed MSc. Okay, nice, nice. So everyone knows group theory, right? Okay. Okay, then shall I start? Okay, so let me start. So as I introduce, the course instructor is Professor Anindya Datta from IIT Bombay. I am also a PhD scholar in IIT Bombay only. And let's start. So I have put in some effort to make this presentation, so you can just see the importance of symmetry in nature, in our life. Whatever is symmetrical, we feel it is beautiful. So symmetry is inherently related to beauty, right? So to study the beauty of the molecule, like different molecules can have different properties, but they may be inherently kind of related in terms of their symmetry, like the point group. Okay, so group theory, it is like to study the point group or the beauty of the molecule in terms of mathematics. Okay, so mathematics, why mathematics? Because we cannot define everything like without, we need some basis to define the beauty of the molecules, right? So to have a basis, we are having this group theory concept. So if you people have know that, like in basic BSc level mathematics course, there itself a course is there which is called set theory or group theory. So that thing we use in chemistry, and that knowledge we implement with to study the molecules and classify them into different point groups, symmetry groups. And so the first thing which we let me put new slide. So the first thing which I want to tell you is, let's have a recapitulation of the week 1 content. So now we have to classify the molecules in terms of their symmetry. So what should be the basis? How to classify it? For any kind of classification, for example our periodic table, it's been classified, different groups have similar properties, right? So for defining the symmetry of any molecule, we need certain basic properties or certain basic parameters on the basis of which we can classify the molecules, whether this is C2, this is C2V, this is D3, the point groups, right? So those, the basic parameters on the basis of which we are defining a symmetry of a molecule, those things are our symmetry elements. Okay? Oh God, let me, my pen is writing very badly, so please bear with it. Something happened to it. It's raining so heavily in Mumbai, every electronics is going bad, so please bear with it. Okay, so symmetry element, first one is our identity element, right? Now identity element, most of us will feel like, what is the need of identity element? Whatever the molecule is. So as I told you, we are classifying the molecules based on a group theory, which is a mathematical concept. So to form a group, we need an identity element. It is the definition of a group that it contains an identity element. There is a question in week 1 content about group, so I'll tell you about what a group is mathematically. So you will be familiarized about why do we need an identity element in the group, right? Okay, let me put my video off. Anyway, it's not being recorded. Is it okay if I put my video off? Okay, so first one is identity element, which we represent it as E. So what happens in identity element? So now one more thing is, as I told, the basic parameters on which we classify the molecule is called the symmetry elements. And whatever a symmetry element does to the molecule, like whatever transformation it creates in the molecule, that transformation is called symmetry operation. Okay, so there are two words, symmetry elements and symmetry operation. So you should not get confused about these two are different things. Elements is the entity, okay, like the plane, the identity element, the point. Okay, so and whatever it does, like a plane what it does, it reflects. A point, we can rotate around a point, or we can flip a molecule around a point. So this flipping, rotation, translation, these things are operation. Okay, so what an identity element does, we can think it identity element as rotation by 360. Rotation by 360 degrees. Suppose if you are standing or sitting and you make yourself a 360 degree rotation, you will get back to the position you are sitting now, isn't it? So basically it does nothing to the molecule, but mathematically we can say that it is a rotation by 360 degrees. Why do we need it? because to complete the definition of a group. Now this was the first. Okay, and yeah, and this identity element is also important because there are many molecules which are so unique that they don't have any symmetry element, but all the molecules will have an identity element. All the molecules will have E, definitely. Sorry, not a vector. Okay, where is my eraser? So I can't find it. So all the molecules will have an identity element for sure. Okay, so next one is our axis. Let's take the plane first. Symmetry plane. This is the second symmetry element, which is called the plane. Plane means a plane. A plane, like you can see my screen, right? This white thing. This is a plane, a 2D thing. Any plane like this. Plane in any direction. And what it does? It reflects the molecule. So a plane put in any direction, we have to specify. Like a plane, it has some axis, right? X, let's put Z, let's put Y. So this is a plane in the XZ direction. So what it will do, it will reflect the molecule. Plane's symmetry operation is reflection. Okay, are you guys following? Okay, so okay, thank you, Vinita. So what I told, symmetry plane, it does reflection. The operation of the plane is reflection. Now like that only, there is one more symmetry element, the third one, which we call proper axis. Proper axis. Axis is what is an axis? Axis is a line, okay, around which what happens? Rotation. Okay, rotation. Now the axis will have an order. For example, axis we denote as C. So if it is an order 1, the order will be written here in subscript. Okay, so this defines the number of rotation, like how much rotation you are doing. Suppose it means C1 means, so total rotation is, for identity, how much you need to rotate? You need to rotate by 360 degree to get back to the same configuration, right? So the proper axis breaks the rotation into certain amount of angle. So if it is C1, it is same as the identity. Okay, C1 means 360 divided by 1 rotation, which is 360 degree rotation itself. If it is C2, it means 360 by 2, that is 180 degree rotation. Okay, so 2 means you have to rotate it by 180 degree, like half of the complete rotation. If it is 3, it is 360 by 3, that is 120 degree rotation. So when we say a molecule has a C2 axis, C2 and this axis, it means when we rotate it twice, okay, here it is the twice word I am getting from here. When we rotate the molecule twice, it gets back to its original configuration. For example, this molecule water. water has a C2 axis, right? We draw the water as like this. So if here is the C2, when we rotate it around this by 180 degree, suppose this is A, this is B, when we rotate it by 180 degree, it will still be this same configuration, right? HB will come here and HA will come here. Don't get confused by the names B and A. They are still H, hydrogen only. I am naming it for my convenience. And when again I will rotate it by 180 degree, we will get back this original molecule, original configuration. A will come this side and B will come, HB will come this side. So this means that this molecule has a C2 axis. C3, can you guess a molecule which has C3? Cn matches with Hn or Sn. C2 matches. Not every Cn will match with Sn. Like C3 is not equal to S3. It is a special case, okay? Not every Sn will match with Cn. I'll come to Sn. BF3 also have C3. Yes. NH3, yes. Okay. Okay, so C3, as you guys told, NH3 ammonia has a C3. Now for symmetry, to get the symmetry of the molecule or to get its point group, it is very important that we draw the exact structure of the molecule as it appears in the 3D world. This plane of the paper or this computer screen or the slide, it is a 2D plane, right? So we can, if I'll write simply like this, NH3, it will work for this molecule. You can see a C3 passing through this, but it will not work for all the molecule. It seems like this molecule is planar here. This is the molecular plane. No. So to get the point group, it is very important that we first know the exact structure of the molecule, how it looks in the three-dimensional representation. So N has a lone pair here and it is like this, a tetrahedral shape with the angles not equal to 109. It is around 104, right? So now you can see it feels like it is three-dimensional. Let me draw these bonds like this also. Okay, my pen is not working good, so you understand, right? This is a wedge, this is a dash representation. Now if I will pass an axis which goes straight like this, and then we do a C3 rotation, then this will be A, this will be B, and this will be C. I am naming it for our understanding. It is not all three are hydrogen only. There is no nomenclature like this. So then it will be for C3-1, when we C3-1 means 1 means applied one time, then it will be N. See my arrow, it is going anti-clockwise. So this A will come here, HA will come here, HB will be in place of HC, and HC will be in place of HA. But important thing is these bond representations won't change, because whatever is up will stay up. So this is this one, this is this one, this is this, and the lone pair is not moving. So here we have HC, here we have HA, and here we have HB. Now why we are calling it that this molecule has C3? Because even after rotation, if I don't place this A, B, C nomenclature here, we can see that all are hydrogens only. If I replace it with, suppose instead of H, I write D. D is what? Deuterium, an isotope of hydrogen. Now we can't say that it has D, because when we will rotate this, here it will be D, here it will be H, here it will be H, and these two are not equivalent configuration. Okay, so, and after 3 rotations, C1, C3 I applied once, then if I again apply C3, that is the second time, then what I will get? The same HB will come here, here HC, and here HA, and lone pair will be here. So this is the second time, and if I repeat this, that one more time I do, then C33, that is the third time I apply, it will be this configuration again. So this will be equal to identity. So if you do it for any, like as I told for water, if I applied C2, water has a C2 axis. If I did C2 once, like this was my C2 applied one time, and then when I do it again, I will get back this configuration. So C22, I will get back this configuration, means that element is E. So the take home message from here is that for any axis, if you apply it equal to that many times, then it will give you give the equivalent configuration as the molecule. Like for example, like the order is N. This number we call it order of the rotation. If the axis order is N, and we apply this axis N times to the molecule, it will give back the identity. Okay, so Cn applied N times gives you the identical molecule. Yes, so this was about the identity. The axis. Now there is one more kind of axis which is called improper axis. This was proper axis. Now improper axis, and we represent it by Sn. S stands for improper and N is again the order. So Sn is a combination of two things, which is Cn. N should be same as Sn, and here the Cn is the proper axis, followed by a perpendicular sigma. Okay, so I didn't tell you that a plane is represented by the symbol sigma. The Greek letter sigma represents a plane, and the subscript here, for example here xz, this will represent the orientation of the plane, the direction in which the plane is oriented. Okay, so improper axis is rotation by 360, rotation by 360 by N, that is Cn, okay, followed by perpendicular reflection. Okay, so now what I mean by perpendicular reflection, okay, I'll show you guys what is Sn. It's very difficult to draw everything here on the 2D thing, and my pen is also bad. I'll show you. Okay, can you see my screen? Which rotation we take positive? Clockwise we take positive mostly, if not mentioned. Okay, so this is a molecule which has improper. Can you identify the molecule? Actually, I cannot see the messages and this screen both at a time, so I'll get back to the messages after a while. Okay, so this is a ethane molecule C2H6, which is staggered in the sense, I will show you the view. So this is a Y, kind of Y, right? As we write the English alphabet Y, this is a Y, and this is inverted Y. Okay, so that's why it is staggered. Eclipsed conformation is in which this also is Y and this also is Y. Okay, so now see how it will have the SN. So this molecule has S6. S6 means it will have a C6 followed by the perpendicular reflection. Simply C6 won't exist in the molecule. You remember this point, that if a molecule has improper axis, the proper axis of the same order may or may not be there in the molecule. Okay, so let's see if it has. Okay, so now it is showing the plane. This axis, the axis you can see in the green color, this is the S6 axis. S6 means rotation by how much? S6 means how much do we need to rotate? S6 means 360 by 6. 60 degree it will be, Sandeep. 360 by 6. Okay, so see, now we have to rotate this molecule along this axis. Remember, we have to rotate along this axis. This is the pivot point. What we call, you have to do it along that axis, not anywhere. You cannot rotate it this side or you cannot rotate it this side. You have to rotate taking care of this molecule. So it will go in this circular rotation only. Can you guys follow my mouse cursor? So I'll show you the rotation. See, now let's see the CS6. Okay, I'll do it again. This is 60 degree rotation, then reflection. So first I was telling rotation around that axis. It is not rotating, it is not flipping here and there. Okay, you need to visualize that. When I was in MSc, I was doing MSc, I had very difficult times visualizing the rotation. So this site is very good to visualize. See, you have to rotate along this axis. Now I'll tilt it. Now see. Okay, first is rotation and then reflection. Now why we are calling it a perpendicular plane? See, the axis and the plane. See, if like this, in this view you can see S6 axis is like this and the plane is like this. So the angle between the axis and the plane is 90 degree. So we cannot reflect it along the axis. Okay, Are you guys following? I hope I'm making you visualize things. Okay, so you cannot reflect it along the axis, you have to reflect perpendicular to the axis you have taken. Okay, then it is an improper axis. So both operations combined is called the improper rotation. So let's see once again. First rotation, now reflection. And S6 minus 1, now minus 1 means the same operation in opposite direction. Now in this one, see how rotation is taking place. It is taking place anti-clockwise, right? This guy is coming this side, so this is anti-clock, and S6 inverse, it is opposite. Now you see this went that side, so this is S6 and S6 inverse. Okay, let's take one more molecule, methane they have given. So this is a methane molecule, the gray one carbon and the white ones are hydrogen, CH4. Now let's look how many S4 operations are there. It has 6 S4 operations. Now let's see one. So it has this S4 axis, it goes like this. This one is C4. Now can you guys quickly tell me S4 or C4 means rotation by how much? $90, right, correct. So we have to rotate these atoms by 90 degree and again reflection. Are you able to visualize? I'm not playing the animation now. Can you just draw the S4? You can share, you can open your video, turn your video on. Reflection followed by rotation. Yeah, you can say both ways. Both are correct. You can first do reflection and then do rotation. Can you draw the S4? Draw stepwise. First either do the rotation operation, then do the reflection operation, or vice versa, your wish. Just draw in your notebook or wherever you are taking notes. Or if you are using tab or anything, you can just present your screen also. If you are done, tell me, then I'll play the animation. Shall I play the animation? Are you doing? Are you drawing the molecule? Guys, okay, so no one wants to respond now. Okay, so I'll play the animation anyway. Let's see. 90-degree rotation, as you told. S4 means first we have to apply C4 and then a perpendicular reflection. Now see, 90-degree, then reflection. Okay, we are getting the same molecule back, no change. 90-degree, then reflection. If you are not following 90-degree, let me show in this view. Fine. I'll play one more time. 90-degree and then reflection. Okay, so this was improper axis. Now there is one more symmetry operation, which is inversion, center of inversion or inversion center. Inversion means this is a point. Suppose if I have, let's take the Cartesian axis. Okay, so this is x, this is y, this is z. It's a three-dimensional axis, and if I have a point here, its coordinates will be in, suppose, x1, y1, z1. Let's not take a point, let's say suppose one entity, one box or one object is here whose coordinates are x1, y1, z1. So if this entity has a center of inversion, means what it will do, it will reflect all the points, all its coordinates into the negative axis, right? So x1, y1, z1 will get converted to minus x1, minus y1 and minus z1. So if this is a center of inversion, these I am drawing the negative axis, so it will be somewhere here in this quadrant. Okay, this is the minus x1, minus y1 and minus z1 direction. So let's take the example of a molecule. Okay, let's take this one. Okay, so this is a molecule which has at 1,3 position 2 halide atoms, such that one is facing upward, one is facing downward, up. Okay, and if I put center of inversion in this one, means suppose we have a center of inversion point here. Now there is a reason why center of inversion is always in the center, because see, this molecule, when you go along this side, when you will try to reflect this molecule through this point, so you have to reflect through a point. This is not a plane, you have to do reflection through a point. So this will go like this, and here again you have the same X atom. Here you have H, here you have H, here you have H, here you have H. So when you will try to reflect the H atom through the point, it will go like this, and here again we are finding H. Okay, this is true for all the atoms. Okay, suppose here this one, this H we will take down, here one H will be there, right? So if you will go in the negative direction, you will find another atom. So center of inversion concept is like, if you go forward or backward, then you have to reach at the similar configuration or similar atom. Okay, so let's take an example, it will be better to show. rather than drawing. Inversion. Okay, so this is a molecule. It is tetrachloroplatinate 2, as you can see. Suppose, okay, whatever it is, A and 4 B atoms are joined on it. Okay, it is a planar one. Now you see the green dot, the big green dot which came. This is its center. This A atom is a white colored atom. Now when I apply inversion, this green thing, it is showing where the center of inversion point is located. Okay, now let's play the animation. You see what happens. So all the atom change places, still the molecule is looking the same as it was before. This is the concept of center of inversion. Now check this. Benzene. See, so symmetrical in whatever direction you see. Now this, and one more thing is, it is not necessary that the center of inversion point of the molecule should be an atom or a bond. Okay, it can lie anywhere in the space. Anywhere in the space means, suppose this is a benzene molecule, this is a carbon atom, this is a carbon atom, this is a hydrogen atom. So it is also possible that for a molecule, for any molecule, the center of inversion point can be here. But for this molecule, the center of inversion point is here. See, it's here, the green dot you see. This is the central point. It is not on the molecule, but it is in space. At some point in space, through which when you will reflect all the atoms, you will get the same configuration back. This is the concept of, for example, in physics you have seen the center of mass concept. Center of mass is, it is located towards the heavier atom, right? And it can be anywhere in space or on the object. Same concept like here, center of inversion, it can be located at anywhere on the atom, on the bond, on the atom, or in space, through which when you will reflect, you will get the same molecule back. So let's see the animation. Woo. So this is coming here, this is going there, same the carbon atoms. So see, from this atom, if you will go forward, you are getting a carbon atom. If you will go backward, you are getting a carbon atom. If you will go forward and little more forward, you are getting a hydrogen atom. And then again, if you will go forward and more forward, you are getting another hydrogen atom. So this is the concept. If you will go forward and the same number of steps backward, you should get the same atom. Shall I play it once more? See, all the atoms are changing places, but still the molecule remains the same. Now again coming to ethane, the staggered configuration. See how the perspective matters. If it is like this, you will be thinking that this is only one carbon is there. But when I will rotate it, and if you see through, you can see there are 2 carbon bonded, and there are 3 hydrogen on that carbon and 3 on this carbon. So now let's see the center of inversion, where it is lying. Okay, for this one, the center of inversion is on the bond itself. So as I told, for this molecule, the center of inversion is the atom itself. You have to reflect through this atom. For benzene, the center of inversion is in the space, no bond, no atom. For ethane, the center of inversion is on the bond. Okay, So the point which I am trying to make is center of inversion can be anywhere in the molecule or surrounding the molecule in the space. Okay, so you really need to have a 3D visualization. 2D will not work, because if it is in space, how will you know? Okay, are you guys following? Okay, so let's see this last one and then we'll move ahead. Inversion, you see how the atoms are getting, this top one will go down. Okay, from here it will cross this inversion point and then it will go here. So while doing the inversion, all the atoms have to cross through this point. It has to reflect through this point. That's why it is, this one is the center point. Once more, you see the top, you just put your focus on any one of the atoms and see how it is going. Okay, it feels like all three are coming here from this side and all three are coming here from this side, and then it is vanishing to the molecule. But what is happening in reality, like one atom is coming to center and then crossing the center and going to the down one. Similarly, this one, the left hand side, this is coming to the center of inversion, crossing it and going to be the down atom here. Similarly for this one. Okay, so I hope I made my point clear. Now let's just see, when I have opened this, so let's see the other examples also. Now, as I told you, identity. What identity does? Basically it does nothing, right? So nothing means rotation by 360-degree itself. So as I told you, if you are standing at a place and then rotate by 360-degree, rotate means rotate in your own axis, then you will find yourself in the same configuration as you were before. So this molecule is a very unsymmetrical molecule. We can say unsymmetrical in the case because it has no symmetry elements present in it. So it has only the identity element. As I told, like in there are molecules which possess no symmetry element, but it must have an identity. So this is a green atom, this is a light green one, this is a red one, this is a white one. So this molecule is this CHF-ClBr. All the bonds are substituted with different atoms. Had it been methane, all four same, it would have been highly symmetrical. Okay, it would have like a tetrahedral point group, highly symmetrical. Now one by one we substitute by different atoms and it is left with only the identity element. See, there is really nothing to show in the identity. This option is also disabled because we can't do anything with identity. It's simply rotation by 360 or do nothing. Similarly, one more, this molecule, this is also unsymmetrical. This is Cl, this is Br. Different. Had been both same, it would have like some symmetry, C2 for example, but here it has nothing. See, you can't apply, you can visualize, right? If you all apply any reflection, suppose if I'll put a plane here along the SO bond, then the green one will go here, reflection plane, and the red one will come here. Okay, which will not be the similar configuration, right? The molecule will not look exactly the same as it is now. So it has no reflection. None of the bonds will reflect, and there is no axis also possible now. You cannot rotate it by, you can simply rotate it by 360 degree. That is only the C1 axis or the identity element. C1 axis is same as the identity element. Okay, so this was identity. Now let's say reflection. Reflection is the most interesting one. So this one, this is ammonia, nitrogen connected to 3 hydrogens. Let's see the reflection axes. So it has 3 reflection. It has 3 symmetry planes on all. Let me hide one. Okay, you can see from this side, it's like mirror image. If you will put a mirror on this plane, you should see exactly the same thing on the other side. If this atom is different, you will not see this same thing there, right? So then that molecule will not have a reflection plane. But this has a reflection plane. If you will put a plane here, you are seeing the same thing on both the side, as if there is a mirror here. So it has 3 bonds and all are equivalent, so it has 3 reflection planes. This one was the first, then the second one, this one, and then the third one, this one. This is the 3 NH bond, 3 reflection plane. Let me show all. Okay, can you see 3 planes? Similarly, how many reflection planes benzene have? Yes, SOCl-Br is similar to NH3, but the first one is most unsymmetrical. Yes, because you can see itself na, all the atoms are different, and they so you cannot have any neither rotation nor reflection along SOCl-Br. That's why ammonia is symmetrical, more symmetrical than that, because it has equivalent atoms. What I was asking, how many reflection planes will the benzene molecule will have? 6. Okay, so as Sandeep is saying, it has 6. Let's see. Let me pull out benzene here. Yeah, got it back. Benzene. Now, so the first one, these are very special planes, and as you can see, it is shown in the red color. The others were shown in green color and yellow color. This one is in red color, so it has some special importance. Can you guess? I'm rotating it all through. Can you guess why this plane is very special? Yes, sigma H. What is sigma? Sigma H? Perpendicular to principal axis. Okay. Now here it is sigma H and also the molecular plane. One thing is, like, all sigma H planes will not be the molecular plane. Okay. For all the molecule it is not true. It is true for this molecule. This is the molecular plane. Now what is molecular plane? Molecular plane means if the molecule is planar, planar means it can be, suppose it can be kept on the table, okay, it's 2D, two-dimensional, without any angled bonds up and down. So if that can be kept on the table, as you can suppose this is a circular table and this benzene molecule is kept on that, then that plane which will reflect all the molecules, sorry, all the atoms up and down. See, when you will turn this upside or downside, it is reflecting, it is cutting through, as if I'll slice it through the plane, the molecule will get sliced half along its molecular axis. So this kind of plane which contains all the atoms of the molecule are called the molecular plane. The molecular plane can also be sigma h and can not be sigma h also sometimes. Okay, so count the numbers. This one is the first plane which benzene have. Let's see how it is reflecting. I'll keep the angle like this. Can you see anything? Why I couldn't see anything? I played the animation, right? I'm playing it again and again. Can any one of you see anything in the animation? Any change? Position of atoms remain unchanged. Right, you are not seeing anything because all the atoms are getting reflected by itself only. Suppose for this hydrogen atom, this one, suppose this hydrogen atom, okay, its first half, left half, is getting reflected by the right half, and it is a spherical atom, okay, so you are not seeing any change. Had it been somewhat like this shape, this side, and then you can see some change, but then this plane will not be the molecular plane. Okay, did you guys follow what I told? So benzene has this special, most of the planar molecules will have this molecular plane. Now next is we will see is the sigma V reflection. Now sigma V, V means it is parallel to the principal axis. Now this is sigma V. Principal axis is the axis of the highest order. No change because the atoms contained by the plane does not move or show any change. That is true, that is true. Correct, Vinita. Now see the sigma V reflection. One is this one. You can now visualize, right, that it is reflecting like a mirror, the left half to the right half. Then if this plane is containing these two atoms, there are four more atom pairs like that, these two and these two, so there will be two more sigma V's, 1 and 2. So these are 3 sigma V planes. Okay, and can you tell the name of that symmetry element where all these sigma V planes are meeting? Yes, correct? It is meeting at the inversion point. See, here we had the inversion center. Okay, so this is about the sigma V, and there is one more type, sigma D, which is called the dihedral plane. Let me remove this. Now, dihedral plane is the plane which bisects the C2 axes, bisects the CN axes. Let me show the, okay, this is, in this molecule it is going through the bond 1, 2, 3. It has 6 bonds, then it will have 3 planes like that, 2, 3. I will show the CN axes also, then you will be okay. This is what my sigma D planes are, okay, going through the bonds. Now let me show you the C2 axes. Okay. Okay, now this is what I want to make you understand, that why it is a sigma D and not sigma V, how it is different from the sigma V. Now you have two C2 axes like this, okay, see in the 3-dimensional view, the C2 axis, the line going through the CH bonds, and this is the other one. Now this plane, what it is doing, it is bisecting the two at the angle between the two C2 axes. This is 1, this is 2, and see, it is cutting it exactly in the middle. So that's why this one is the dihedral plane, cutting two C2 axes. And now I'll show you the sigma V. You remember where the sigma V was? Sigma V was the plane along the C2, you can say. Okay, these two are sigma V's. See, now you get the difference. Sigma V and sigma D. So the molecule, this benzene molecule, 3 sigma V, 3 sigma D, and 1 the molecular plane. Total 7 planes. Got it? Okay. So what I was telling, reflection. Now again, now let's see rotation. The last example, then we will come to the assignments. Now water, the most common example, it has C2, right? C2 going through the oxygen atom. Okay, this is the C2. And as I told, for center of inversion, that it can be on the bond, it can be in space, or it can be on the atom. Similarly, for the axis also it is true. Okay, it can be anywhere, it can go from piercing the bond, or it can be in the space as well. For example, for benzene, the C6, see, the C6 is here in the space. It is not going through any atom, right? So this is true for axis also, inversion point also. Okay. Now coming to one more, ethane. Again, the staggered ethane, it has both C2 and C3. Let's see which one will be the principal axis here. Why? Okay, now we call that axis as a principal axis which has the highest order. Okay, and if all the axes have the same order, suppose a molecule it has 3 C2 axes only, then the one of those C2 axis will be passing through most number of atoms in the molecule, then that axis will be named as the principal axis. Okay, and it is always better to write the direction. Suppose if you are writing C2, then write it as C2x, C2y or C2z, in which direction it is going. Now here C3 is the principal axis. Now let's see C3. Okay, let me show them. Here there is no confusion because it is two different orders. C3 has the highest order, so C3 is the principal axis. So see the rotations. C3 means rotation by how much? Quickly, yes. Okay. 3 means 360 by 3, which is 120 degree. So you can see from this view, see the top carbon, see the top carbon only, this bond angle, it is 120 degree. So when I'll put C3, okay, this atom is coming here, it is going there, this one is going there. So this one is C3. Similarly for the back carbon as well. This is C3. Now we'll see where the C2 is. Let me hide C3. C2. So many C2s. Let me hide this one. See from the top view. Okay, are you guys able to visualize now? I am doing 180 degree rotation, suppose along the Z axis for this molecule. So I have to flip it aside. Okay, if you are holding it in your hand, you have to flip through the axis. So these two will go down, this here up will come down here. Okay, you follow my cursor, this two will go down here. Okay, let's see, notice any one atom. Suppose we will follow this atom and we will look where it is going. Saw it, right? Now let's see the other one. Let me hide this one. See in this view. Okay, these two bonds, these two up are becoming this one up and this one down here. See carefully. Okay, and similarly one more from this side. This is the, see from here, this angle. Okay, we are rotating along that axis, flipping along that axis. Not flipping, flipping is rotating along that axis. So these two here are coming, these two. 180-degree rotation. Okay, did you guys follow? C to X, Y, Z. Yes, correct. Okay, now let's come to the assignment part. Did you guys solve the assignments? You solved the assignment, Ayush? Yes, yes, okay. Okay. So we will go through the assignment, we'll check the solution first, and if you have done any mistake, you can just learn now. So I'm discussing the week 0 assignment first. So the first question was, this molecule, as I shown in the example, a planar molecule with two substituents, one up and one down on 1,2 position. So for the molecule given above, symmetry element that are not present. So the element which is not present. So now I'll have to draw this. Let's see point of inversion. This is my molecule, and if I'll put a point of inversion here in between the molecule in space, then I have to reflect through this point. So suppose if I'm going to replace this atom, so when I'm moving backwards through this point in space, I'm moving backward. Now here there is nothing, this is empty, there is no X atom here, so this definitely does not have a center of inversion. Similarly, when you will look for this atom, when you are moving through this point and across this point in space, here there should be some atom. Okay, not some atom, there should be exactly the same halogen atom, but it is not there. So the molecule, it does not have a inversion center. Now look for C2 axis of symmetry. Now where the C2 will be, you have to check through all the direction. Okay, now if I'll put a C2 like this, like through this plane, okay, if I'll rotate 180-degree in plane, I am not changing the plane, the plane is there only and I'm just rotating. So it will become, suppose I name it XA, XB, 180-degree, this will come here and this will go there. So sorry, 180-degree XA, and not here, it will go here, XB, and this is not an equivalent configuration. Okay, now let's see if I put a C2 XA, XB, if I'll put C2 which is in the plane, so this is my plane and my axis is on passing through the plane and I have to rotate like this. So XA, which is up, when I will flip it 180-degree, out of plane rotation I am doing. So it will be like XA, which is up, it will come down, XA here, and B, which is down, it will go up. Okay, so this was second, and one more direction is left. XA, XB, okay, this direction will be, if I'll put C2 here and I have to flip like this, C2, here it is up, it will go on this carbon and it will go down, XA, and here it is down, it will just flip and go up. Okay, XB, and this is also not same as this one. So when I will write it like without A and B, here it is X, here it is X. Now you see the positions have changed. If I'll do the nomenclature of positions, the positions on which we had substituents, it changed, right? So this is not equivalent configuration. But if I'll show you this one, here what happened? Here when I kept C2, 1, 2, 3, 4, if I'll name them, and here again 1, 2, 3, 4, this is same. This A and B is, for my understanding, that this atom went here and this atom came here. Okay, this is for our understanding, but actually this is a halogen atom, this is a halogen atom, and two halogen atoms, the same, suppose it is chlorine, the two chlorine will be identical. Okay, one chlorine atom cannot be distinguished from the other one, right? So this one is an equivalent configuration. Okay, so we will say that C2 is present along this direction. So this was C2Z, this is C2X, and we'll name it this one as C2Y. Then we can say that C2X is present. Okay, are you guys following? But the molecule is not visible in the week 0, just question is visible. Okay, there may be some printing mistakes, Vinita. The molecule is this one, you can solve it now. You can solve it now, it's okay. Anyway, week 0 assignment is not graded, so don't worry about it. You can just solve it now. This is the molecule. Disubstituted cyclobutane. So now we have proved that it has C2. C2 is present. But the question asks which are not present. So this cannot be the correct option. C2 is present. Now let's check for C4. Now X. So I'll simply show that C4 is also not present. C4 means I am putting C4 through this, that is C4Z. C4 means you have to rotate it by 90 degree. So 90 degree rotation, here we will get XA, and this will go here, here we will get XB. okay, in plane rotation. If you will do out of plane also, the molecule will not be planar. So if I will do out of plane, suppose this is my molecule, here X, here X. If I will put C4 in this direction, so I have to tilt it by 90 degrees. So the molecule will be in the plane of the paper, right? And one atom will be here going down, and the other, sorry, here only going down, not this one, and this will be, this is up and this will be down. So the molecule will just get from horizontal, it will come to the vertical plane. So this is also not there, and similarly in this direction it will get tilted in the other side. So this is also not there. So C4 is not there. So C4 can be one of the answers. So C4 is true. Now let's see for mirror plane. Okay, here I have to put reflection planes. If I'll put a reflection plane in, as it is a planar molecule, I can keep a plane which is parallel to the molecule, which is containing the molecule. Okay, so then what will happen, since this one is up, in the reflection in the mirror it will go down, and this is down, it will come upside. Okay, so this is not an equivalent configuration, it is changing the stereochemistry. Okay, our goal is to get the equivalent configuration without changing any stereochemistry, without changing the position of the atoms. So this is not equivalent. Okay, then suppose if I'll put plane, this is sigma z. Okay, if I'll put sigma x or sigma y, then let's see what happens. If I'm putting a plane like this, this is a plane sigma y. Okay, then what will happen, this is a mirror like this. Okay, this will get reflected to this side, this will get reflected to this side. So this down x will come this side, this will come this side. Now sigma y is also not giving the equivalent configuration, so sigma y is not present. Similarly you can check for sigma z, sorry, sigma x. Sigma x, what it will do, sigma x will be like this plane. Okay, this will come here, this will go there. This will become down, this will become up. So here also the atoms are not changing at the like carbons, but their stereochemistry is changing, so it is also not equivalent. Okay, so we have seen all the planes. So it doesn't have a mirror plane, it doesn't have any mirror plane. So this can also be the correct answer. Okay, so our three options which are correct for this question is A, C and D. 2 is not correct because the molecule possesses C2 excess of symmetry. Okay, okay, Now let's, yeah. Now the second question is, for an H2O2 molecule, both in the cis-planar and the trans-planar conformation, C2 is present as the principal axis, possess sigma H, possess sigma V as two axes of symmetry. Okay, so let me first show you this molecule O2A H2 in transplanar and cisplanar. It will be like this. Trans means like this and cis means on the same side. Okay, and it is a planar molecule in the plane. So when you will keep C2 here in the plane, it will definitely, sorry, not in the plane, along perpendicular to the plane. This is a C2 perpendicular to the plane. C2Z. Suppose my molecule is in the XY plane. Then when you will rotate, this O will become this H will go to this. Okay, you need to visualize a little bit. Let me show you this molecule in this. I think I have. So here it is, H2O2. Now let's see, this molecule is, I am telling you, this is not the planar one which is asked in the question. Okay, can you see the bonds are twisted? This is, the bonds are angled. It is not the planar one, but for your understanding I am showing you this molecule. It is called the open book structure. When you will see through this angle, if you will keep a book open, the two like the hard covers of the book angled, you will have a kind of this structure, open book structure. So this one is not planar, but I'll show you how C2 is acting on this. You can similarly imagine C2s for the planar ones also. Now this is the C2 rotation. Okay, out of plane. You can think for the planar, this one is the plane of the molecule, and it is rotating out of plane. Okay, got it? But H2O2 is non-planar. Yes, that's what I am saying. I am showing you the non-planar version, which is the actual molecule, but this question is hypothetical, and it is asking you if it is planar, how it is asking you to imagine what would be the symmetry element present when it is planar. Okay, so if it is planar, it will have in the cis-planar and the trans-planar configuration, it will have the sigma H, C2 will be present, sigma V will be present in this only. Suppose this one sigma Z. So when you are reflecting along this plane, Okay, this is the plane, a vertical plane. When you are reflecting, these two will reflect, these two will reflect. It is present in the cis, but it will not be present in the trans. So it is asking both. So this is not true. Now S2, when you will reflect S2, it will be present in the cis, but it will not be present in the trans. Suppose it is here and then you rotated it and then you are reflecting. Yeah, S2 is also present. S2 is also present. This will be the perpendicular plane, which will be the molecular plane. S2 will also be present. Now C2, this and this, both in the cisplanar and the transplanar conformation. Okay, so let's move to the next one. We have the product of the following matrix multiplication. Now this is very simple. You must have learnt matrix multiplication in the 12th standard or BSc. Now what we do, we multiply element by element. So suppose this is a 2 cross 2 matrix 1 and the other one is 2 cross 1 matrix. Why 2 cross 2? Because it has, this is first element is rows and second element will be column. So this has 2 row and 2 column. Row is this one, column is this one. And this one, the second matrix, it has 2 rows, 1, 2. But there is only one column, so it is 2 cross 1. For matrix multiplication, the number of columns of the first matrix and the number of rows of the second matrix should match. So here it is matching 2 in 2. So the resultant will be 2 cross 1. These two, you can think that these two will vanish and these two left over will be the resultant matrix order. Okay, so you can see, you can simply cross these two off because it has 2 cross 2 order. So these two are wrong anyway. These two may be correct. It has 2 row 1 column. Again this one also 2 row 1 column. Now let's multiply. So first we will multiply 3 by 4 and then addition. Then we will multiply 2 by 6. This is my first element. The second element will be 5 multiplied by 4 plus 8 multiplied by 6. Okay, now you can do the maths. 12 plus 12, this is 20 plus 48. So the answer is the third one, C. Okay, I hope you guys are familiar with matrix multiplication and all. Okay, okay, let's move ahead. The third one, the property that is not necessarily required for a group is closure, commutativity, associativity, identity. Now this is what I was telling in the beginning of the class, that I will first tell you what a group is. Now group is a mathematical concept. It has not come from chemistry point of view. It is mathematical concept, group. Now what is a group? Group has two elements. First of all, one is the operation, one is set, one is operation. Okay, operation means any binary operation which needs two things to operate on, two entities to operate on. For example, plus minus, division, subtract, multiplication. Okay, these are operations, and set is the set of entities on which the operation will be carried out. For example, we can take set of natural numbers, set of integers, set of real numbers, set of whole numbers, anything. Okay, so I'll give you an example of a group. When we call something a group, now set of integers under addition forms a group. Now, as I told you in the beginning, we need a basis to classify things into certain categories. So what are the basic categories for a group? Now, first property for a group is closure property. We call it closure. What does closure means? Closure means that the operation which you will perform on two elements of the group, you will get a result. Suppose my operation here is addition, and my set on which I will perform the operation is integer. For example, 2 plus 3. These two are in integers, which is coming from my set. My set is integer, and this is the binary operation which I am performing. The resultant is 2 plus 5. What is the result? 5. Now what is 5? 5 is also an integer, right? 5 belongs to not zi. Okay, 5 belongs to the set itself. So whatever I perform on the set and the resultant belongs to set itself, then if any group follows that property, then it is called that group has a closure property. That set is closure. So let me write it. The result of the operation on A and B. So this is my A, I am taking it as A. This is my B, and my operation I am giving it a symbol star. Okay, star can be any operation: addition, subtraction, multiplication, division. In our case, we are studying molecules, so star can be rotation, reflection, inversion. Okay, like that. So the result of the operation on A and B, which is A star B, whatever will be the result should be an element of the set itself. Okay, so this is called the closure one. The second property is associativity. So associativity means whatever order you perform the operation, you will get the same result. So as one student was asking, if we perform reflection first or rotation first, it does not matter, you will get the same result. So similarly, associativity, it is like if you will do 2 plus 3 plus 1 will be equal to 2 plus 3 plus 1, right? We will first do 2 plus 3, which is 5 plus 1, and then here we will do 2 plus 3 plus 1. Bracket means I have to do this operation first, then 3 plus 1 is 4. The answer will be 6, na? In both cases. So this property is called associativity. So the order in which binary operation is performed does not affect your result, does not affect the result. That is, if we will represent it, A star B star C is equals to, A if I'll perform B cross C first. So if any set under operation star follows this criteria, then it will be said to have associativity property. I will give you an example for a set which does not follow this criteria. Let's take example set. I will take natural numbers. Natural numbers. Now what is natural number? Starting from 1, right? And we will take the operation here as subtraction. Okay. So if I will do 1 minus 2, this is a natural number, this is a natural number, this is my operation. So what will be the result? 1 minus 2. Yeah, okay Vinita, that's why I am explaining these things. So you can just tell them what is 1 minus 2. 1 minus 2 will be minus 1. Basic mathematics, 1 minus 2 will be minus 1. But this is my result, minus 1. Does minus 1 belong to the set of natural numbers? My natural number is starting from 1. It doesn't contain 0, minus 1, minus 2. It doesn't contain the negative number. It doesn't contain 0. But here what the answer which I got, 1 minus 2 is minus 1. It does not belong to this set. So the property it is violating is closure. It is not close. Close means packed. Whatever result you are getting should be packed in the set itself. But here you are getting minus 1 which is not there in the set. So the set of natural numbers under the operation of subtraction is not a set. Okay. Also let's see the associative property. It will not follow the associative property as well. Suppose if I do 1 minus 2 minus 3. Okay, the result should be minus 1 minus 3. Minus 1 minus 3 is minus 4. Minus 4, first of all, it does not belong to the set of natural numbers, which means it is not closure. The second, I will perform 1 minus 2 minus 3 first. So the result will be 1 minus 2 minus 3 will be minus 1. So 1 minus minus 1 is plus 1, which is answer is 2. So you see the answer got changed. When I did 1 minus 2 first, it was minus 4. When I did 2 minus 3 first and then subtracted it from 1, the answer was 2. So we are getting different answers depending on the order of operation. Okay, so this set is not associative. Are you guys following even a little bit? Okay. Yes, Vinita, minus 1 does not belong to the set of natural number. So it is not following the first condition itself. The first condition Closure, it is not following. Associativity, it is not following. So it is not a group. But the first example which I gave you, which was the set of integers under the operation of addition, that is following. So we can, till now we can say that integers with addition is following closure, is following associativity. So it can be called a group. Now there are two more criteria for anything to be called a group. Now let's see those. The third criteria is identity element. Now you will get to know why our identity element is there. Why do we consider it as a symmetry property? Identity element, what it does for let me write it first and then I'll explain you. You will get it easily. For any element A, there exists an identity element E such that A performed that operation. Star means my operation. A operation E is equal to E operation A is equal to A. Okay. Whatever operation I do with the identity element, it should give me back the same element, right? Suppose, what was our set? Integer with addition. Suppose I have 10 here. 10 plus. What shall I add here to get 10 again? Can you guys guess? What shall I add into with 10 to get 10? 0. Very simple, very easy. We have to add 0. We have to add 0 to it to get 10 again. So 0 is identity element for this set and this binary operation. Okay. You can add anything to 0, it will give back the same element. Suppose I add 2 plus 0, I will get 2. I add minus 1 plus 0, I will get minus 1. So 0 is the identity element, and also 0, it belongs to the set of the integer. What is my integer? Negative numbers, minus 2, minus 1, 0, 1, 2, 3. So this identity element is itself the member of the group. Okay. So that's why we have the identity element in our symmetry properties. That element has to be there for something to complete a group. We say that point group, isn't it? We say that ammonia has a point group of C3V, water is C2V. That is a group. Group is a mathematical concept, and to follow the criteria of a group, the identity element should be there. That's why we have the identity element E in it. Okay, got it? Now let's move faster. We have the element, the fourth criteria, the fourth and the last criteria for a group to be called, for a set with an operation to be called a group, is inverse. Okay, inverse element. As identity element, we have inverse element. Now what inverse means? There exists an element A inverse. Superscript minus 1 means inverse. It is all mathematical every operation is a matrix, and in matrix we represent inverse like this, superscript -1. Okay, in the upcoming weeks you will get to know how we write, like we did reflection, we did rotation to a molecule. Everything can be represented in terms of matrix. Okay, so that's why we are using matrix representations here. There exists an element A inverse for every element A such that A operation A inverse should give you equivalent thing as A inverse operation A, and it should be equal to E. What is E? What is E here? What is E? Identity, right? So there should be some element A inverse such that when we are performing that operation with A, we should get the identity element back. Suppose now I'm again taking the integer set with positive plus operation. Now I have to get identity. Let's take example again, 10 plus something I should add here to get my identity. Identity was 0. Okay, here only we saw identity element is 0, so I have to get 0. What to add here? What to add? Yes, we have to add -10. Is -10 element of the set? Is -10 element of the set? Set is, our set here is integer. Is -10 set of integers? Yes, it is. So -10 is a valid entity. We can add -10 because -10 is an element itself in the set. So we are not taking anything out from outside. We have the set of integers. We are taking -10 and we are adding it here to 10 to get my identity element. So like this, for every element you have 20. Then there exists -20 which you can add to give 0. Suppose you have -30, then you can add into it 30, which is the element of the set of integers, to get 0, which is identity. So this set of integer under the operation of addition is following all the criterias, which is closure, associativity, identity element, presence of identity element, and presence of inverse element. So that's why this set with the addition operation, set of integers with addition operation forms a group. Okay, now we came to the term group. Now it has become a group. Otherwise it was simply a set. For example, this natural number, this is simply a set and an operation. Combining these two is not forming a group because it is not following the properties of closure, not following the properties of associativity, not identity. There does not exist the identity element for this. Okay, so this is the definition of a group, mathematical group. Now let's come back to the question. The question was, the question is the property that is not necessarily required for a group. The properties which is not necessarily, it can be present but it is not necessary. What I told you, I told you closure, first property. I told you associativity. I told you identity element. These three plus inverse, these has to be there. If any one of them is not there, then it cannot be called a group. Okay, so these three are must properties. But what I did not tell you is the commutativity. Okay, I think these things we have studied in 6th or 7th class maths, but let's revise again. Commutativity, it is not a necessary property of a group. If a group is not commutative, still it can be, if a set is not commutative, still it can be called a group if it is following the other four operations. Okay, now what is commutativity? Commutativity means the operation the group is said to be commutative if A star B, A not star, A operation, we read it as A operation B is equals to B operation A. Okay, what we now here we have to look through the symmetry point of view. In symmetry, everything is a matrix. Okay, now here we will have a matrix of reflection. Okay, and here we will have matrix of rotation. So if we multiply these two, okay, then we will get some operation which will be our configuration when these two operations are performed on the molecule. Now matrix multiplication is very sensitive to the order in which you are performing. This we all know, that matrix multiplication depends on the order. Suppose we have m cross n into n cross k. This matrix multiplication is possible, and because these two are same, number of columns of the first matrix and number of rows of the second matrix are same, so we are getting m cross k as the resultant. But if I'll change the order, n cross k into m cross n, then this is not possible. This multiplication cannot happen because these two are not same. It will not be operated on the molecule. So this property A star B is equal to B star A, this property follows only in certain conditions, not always it has to be true. Okay, so that's why commutativity is not the essential property. Okay, I think it's time now. I will wrap it up here. So the answer to this question is, question will be the B1. Okay, commutativity is not required. It can be there, it cannot be there, it does not matter. Okay, did you guys follow? Okay, thank you for the thumbs up, Sandeep. Please share the slides. Okay, yeah, slides will be there. Did you guys receive a public sheet, a Google sheet or something? In that sheet there is a link for the course, and the course the whole session's recording, it will be there on YouTube channel also, so you can just, if you want to visit, you can go through. Okay, I'll end this session. Is it fine? or you can ask the doubts regarding this in the next week's session. And I thought of completing week 1 and week 2 assignment, week 0 and week 1 assignment, but I could not do. I'll do it in the next week. So we have so many questions left, and here is something you can practice. I have given some molecules and some point groups also there. As I know you guys are MSc students already, so you can just practice these. Okay. I'll end the session. Thank you everyone for attending. Let's meet next week, next Monday, same time. Good night.